Welcome friends, we will talk about the 26th lecture. Where we will address the stochastic process and then move on to fatigue reliability. This is 26th lecture in module 2, where we are focusing on structural reliability, this is an online course titled Risk and Reliability of Offshore Structures under NPTEL IIT Madras. In the last lecture we discussed that stochastic process can be qualified as a random process or stochastic variables can be qualified to be called as a random variable provided they are selected in the interval T1, T2 etc., where T is a space of index set. As an example, we applied this indication as a realization of this process on a Gaussian process, and we also showed that Gaussian process will remain strictly stationary. One important issue related to stochastic process is what we call as barrier crossing. Now, what is a barrier crossing issue? For a stochastic process, it is very important to know the number of crossings of a given threshold value, what we call barrier. So, in a stochastic process, one will be interested to know the number of crossings of the variable over the barrier value. The barrier value can be any value of the designer's or analyst's choice. Once this value is fixed as a barrier or an upper limit, one would like to know how many number of times the variable has crossed the threshold value. Now, interestingly, the extension of this is essentially applied to what we call fatigue reliability. So, this is very useful to obtain the direct delta function. Which can be now done indirectly. Let us try to understand the realization of a stochastic process again. Let us say we draw a stochastic process variable, the space of event or the index is T. Let us say a signal typically looks like this. Let me draw a threshold value which I am going to indicate in my analysis. Let us say this is my x of t. Well, the threshold value is marked in this color. I call this, let us say x of t is equal to some value which is z. Now, I want to mark the threshold crossing values. Let us say 1, similarly 2, 3, 4, 5 and so on. Let us say we start the signal varying from the limits t1 and the signal ends at the limit t2. Now, to solve the problem of estimating the expected number of positive passages, why it is called positive passage? I am looking only the upward crossing. Okay, this is actually not touching the value. So, it is not crossing the barrier. I am only trying to mark the upward crossings in the given system. Now, to solve the problem, of estimating the expected positive passage in terms of its numbers of a given barrier in this case the given barrier is a fixed value zeta. We look for Heaviside step function. The Heaviside step function h of x is said to be 0, half and 1 for different conditions, for x of t less than 0, for x of t equals 0, for x of t greater than 0. I will call equation number 1. By a formal differentiation of this function, one can easily get the Dirac delta function. Which is indicated as delta of x. Now, the advantage of that method of obtaining Dirac delta function is only a definite set of values can be assigned to x. Okay, can be assigned to x, which is given by the Dirac delta function of x limit zero 1 by 2 pi epsilon e to the power of minus x square by 2 epsilon square. Equation number 2. So, one can easily find the Dirac delta function, which has an advantage of having the qualified definite set of values which can be assigned to the variable x in a stochastic process, provided we will be able to find out the number of positive passages using the Heaviside function as we just presented in equation 1. Now, the next concern about the stochastic process is the peak distribution. Because this is another concern, otherwise in general in probabilistic estimates using random variables. Now, the results derived from barrier crossing can be used to investigate the statistics of the peak distribution? Of the stochastic process. In our case, the stochastic process, what we are talking about is x of t, where t is a subset of capital T, which is called the index set. Interestingly, the peaks and troughs occur when the stochastic process has a 0 crossing, the number of 0 crossings of this process is equal to the number of extremes in the given process. In x of t. If x of t is a narrow band Gaussian process, then distribution of peaks can be determined in a very simple manner. The expected number of peaks above the level. In our example of discussion, we say the level is zeta and we want to say zeta is more than 0, we are looking for the positive passage. So, the expected number of peaks above the level zeta per unit time is actually equal to the expected rate of crossings of the barrier zeta. Which is actually equal to the expected value of n prime plus of z. Similarly, the expected total number of peaks per unit time will be equal to the expected rate of 0 crossings which will be simply E n prime plus 0, because we are looking for the positive passage. Therefore, the expected relative number of peaks above zeta per unit time is given by expected number of peaks as given by this value divided by expected number of peaks as given above 0, which is same as minus zeta square by 2 sigma square. Let us call this equation number 2. The distribution function which is f equals of zeta for the peak magnitude for the condition zeta is more than 0 is given by f function of zeta is 1 minus e zeta square by 2 sigma square. There is a minus sign here for 0 less than zeta less than infinity. Which we call as equation number 3. The corresponding density function which is of zeta is given by we will talk about small f here, density function, distribution function capital F. Okay. Zeta is given by zeta by sigma x square e to the power of minus zeta square by 2 sigma x for zeta 0 less than zeta less than infinity, equation number 4. Interestingly, equation 4 will expected to follow a Rayleigh distribution. So, friends, instead of handling a random variable, we alternately picked up a stochastic variable which can be expressed in a space set capital T, what we call as an index set. When the realization of this process happens, we can always check the positive passages of this variable with respect to any predefined threshold value, what we call as a barrier. We can always find the barrier crossing rate as expressed in the equations given to you on the blackboard just now. This can be applied directly for fatigue reliability. So, the concept what we discussed so far as the barrier crossing can be usefully applied directly in fatigue reliability analysis, which we will discuss further. I will also take up a case study where we have estimated the tubular joints capacity, which can be one of the important input for reliability analysis of offshore structural joints. So, let us now expand our discussions further with the background of stochastic process on to fatigue reliability. Discrete wave and spectral methods are used generally for fatigue analysis. You can have two ways by which it can be done. One is what is called discrete wave approach, other is spectral method. We all know fatigue is a very important consideration in the design of offshore structures, especially when the connections are welded in steel construction. So, as indicated by ABS, American Bureau of Shipping 2003, 2004, fatigue is an important consideration in design. Of offshore structures where the members are essentially steel, where steel construction is welded. So, we are talking about the welded joints and its capacity to resist the loads in terms of reversal of forces. Different parameters will affect this. Different parameters, for example, sea state complexities, complexities involved in modeling, hydrodynamic loading, let us say structural behavior under combination of forces. Will govern the fatigue failure. Especially when you look for the dynamic response behavior. So, friends, one can easily understand here fatigue reliability can be handled with the input variables as a stochastic variable, taking time as an index set, because we are looking for the dynamic response behavior which is predominantly affected by the factors which can result in a fatigue failure. So, if you ask me a question, what is the direct influence of fatigue on the joints of steel construction, it results in what we call stress concentration in tubular joints is the direct consequence of fatigue loads. Now, there are various difficulties associated in estimating the fatigue failure in offshore structures in terms of its reliability in offshore structures, as indicated by Arulia 1976, American Building Society 1972. You can also look at Baldrop and Adams in 1991. So, researchers have indicated several set of difficulties which are associated in estimating the fatigue reliability, especially or in particular to offshore structures where the joints are essentially tubular. Now, one is interested to know what is the fatigue damage caused by the set of loads on the given system and what would be the probability of failure if the fatigue load exceeds the number of cycles of sustainability of this kind of reversal of loads by the material or by the joint configuration. So, one is interested in understanding or identifying what we call fatigue damage. This can be assessed by two methods. One is the discrete wave approach, as we said in the beginning. Other could be the spectral approach. Discrete wave approach consists of simplified probabilistic models for the wave environment. It is a simplified approach consists of simplified probabilistic models. It uses the recommended set of waves for specified amplitude their frequency, the number of cycles of occurrence or the stress range distribution. As suggested by the literature, the references can be Ding et al. 2005, Ferry Box and Castaneda 1971. So, discrete wave approach uses specific amplitude of waves, the frequency content, the number of cycles or the stress range distribution for estimating the fatigue failure, which is more or less a simplified approach suggested by the researchers. Alternatively, if you look at the spectral approach, it employs a random process model for a short term C state. It looks for an array which are constituted for a long term wave environment. So, looks for a random process model for a short term C state. In case of long term C state, it uses an array of the random vectors. Now, the random process or the C state is typically represented by what we call wave scatter diagram or bivariant histogram. We all understand and agree that the predominant load acting on offshore structures is wave loads. Cyclic stresses caused by these kind of loads induce fatigue damage in offshore structural members, especially at the tubular joints of steel jackets and towers. Since they have very high stress concentration zones, the fatigue damage is generally aggravated by the possible dynamic amplifications caused on the structural response as well. So, here the fatigue damage is triggered due to or triggered by the dynamic amplification happens due to the structural response Now, interestingly, we have form dominated structural systems in the recent generation. The structural responses are going to be very high, and the dynamic amplification, if not designed properly at certain frequency bands, will be phenomenally or significantly high. So, the damage caused by the stress concentration factors at the tubular joints because of reversal of forces or reversal of amplitudes or directions of wave load acting on these members will cascade the effect of failure in the presence of larger responses, which amplifies the failure because of the dynamic amplification factor presence in the given system. So, therefore, fatigue analysis or failure due to fatigue loads or in general fatigue assessment in offshore structures consists of establishing a fatigue demand of the element. Okay. Then compare it with its fatigue strength. If you look at this whole statement closely, this is nothing but the basic concept of reliability. You know what is the strength of the member or the material, you know what is the demand or the action applied by the forces on the member. So, when you are able to estimate the fatigue demand of the set of structural elements in a structural form of an offshore structure and also able to compare it with the fatigue strength of that members or the structure, then one can always assess whether there is any probability of failure caused by the fatigue loads, what in general we call fatigue reliability, as suggested by Goodwin et al. 1999, Hassan et al. 2009. So, this is nothing but a broader base or what we call fatigue reliability. Considering the stress ranges, the material or the member can withstand, which is denoted or which denotes, let us say, the absolute sum of cyclic stresses. Or one can say even cyclic stress history about a mean stress. Fatigue demand is nothing but is a quantification in terms of stress ranges. Experienced by the member due to various load combinations. Basic fatigue data is actually the relevance to SN curve. Basic fatigue data has a very strong relevance to the SN curve. SN curve actually represents the stress range and the cycles of failure. So, S is the stress range and N is number of cycles to failure. SN curves are generally generated using appropriate experimental data. Of course, this is verified by many literature proof. If you look at Haver et al. 2001, Hode et al. 1997, they have commented upon the limitations of the SN curve obtained from the experimental verifications. If you look the whole discussion in the context of offshore structures, we understand the primary source of loading in offshore structures arise essentially from ocean waves, which is cyclic in nature. So, now the description of the input load which is going to cause a cyclic effect on the offshore member can be described in two ways. So, the cyclic load which is causing fatigue damage essentially comes from wave loads predominantly in offshore structures. Of course, various researchers have experimentally, analytically examined and verified this statement. As suggested by these researchers, the cyclic load effect caused by the waves on offshore structures can be described in two ways. One, again using a discrete wave approach. Alternatively, using a stochastic model. The discrete wave approach deals with non-deterministic nature of wave heights. Whereas the stochastic model approach represents C state in spectral character, which is more realistic. Therefore, the second method is most probably and commonly used for fatigue assessment in offshore structures, as suggested by Madhavan Pillai and Veena in 2006. Let us say we want to represent the cyclic load caused by the wave effects on the structure by any one of these methods. Now, what is the major task as far as we are concerned in fatigue assessment? The major task in fatigue assessment is to compute the stress concentration at critical points, what we call as hotspots. So, at these points fatigue damage will be estimated. In particular, we have to establish a relationship between the wave height and the stress concentration. So, the whole focus is to establish a relationship between the wave amplitude and the stress, what we call SH relationship. At critical points, essentially the hot spots. So, the whole exercise of fatigue assessment is converged to estimating or computing the stress concentration at hot spots. So, we need to establish a relationship between the stress and the wave amplitude. To do this, various steps are involved. We will discuss this in detail in the next lecture. We will further elaborate the fatigue assessment in terms of fatigue reliability applied to offshore structures. Then we will take up a very specific example of estimating the stress concentration factor for tubular joints of different structural forms of geometric forms, which has been done experimentally, and then we will compare them with the empirical relationships given by international codes for our better understanding. Therefore, one can then explicitly understand the limitations of estimating the stress concentration factor, which is one of the vital requirement of fatigue assessment in a given tubular joints of offshore structures. Thank you very much.